I would like to give the floor now to Dávid Raisz. David has been working at the Department of Electrical Power Engineering since the year 2000, with 5 years of experience at the E.ON Energy Research Center at RWTH Aachen University in Germany, as well as Graz University of Technology in Austria. David has established new research areas at the university, like electricity market modeling, application of power electronics in power systems, and power hardware in the loop modeling in the power system domain. As the head of the Smart Power Lab, he is leading R&D projects with industry partners, as well as visionary research projects, both national and international. The floor is yours.
Thank you so much. Okay, welcome everybody, and thanks for having me here, and thank you for following these discussions or presentations online and offline. I'm talking about energy, and I'd like to start off with a quite bold statement. So whatever is happening in the energy industry is, I would say, far beyond the imagination to the non-professional community. So everything that's going on behind the socket, it's really a dramatical change in the energy and the power sector. And what we usually see from that is more and more solar rooftops, and also our bills are getting more and more complicated over the years, and our contracts with the suppliers. But apart from that, we probably not really understand what's really going on in that sector. And these changes that I'm talking about, these are mainly, well, partly technology driven. So many new opportunities are arising from technology, be it semiconductor technology or communication technology or measurement and data and sensors technology. So and on the other side, it's also demand driven. So and also driven by the wish to make the power system more sustainable than it was so far. And if we, I mean, you observed the second presentation today. A good indicator of these challenges that we have ahead is that the regulation, so the legislation and all the defining the new roles in that sector, and also defining the new structures, it's lagging behind. So technology and demand and all this development is so fast that the regulation is really they're really struggling to catch up with all this development. And what my team wants to achieve really is to boost local industry mainly, and make it more of a leader and not a follower. Because you see, in the energy industry, the main players are large international companies, and they are supplying technology mainly, and they are supplying all the solutions that are composing this very basic infrastructure that we have. And apart from that, there is an emerging or a new field is opening for small companies as well, and we can see that mainly in Germany, but also in other countries around Europe that are very innovative and that are able to deliver new ideas into products and following this chain that we have heard here today before. So that's what we would really like to help boosting in the Hungarian sector. And I believe that there are two main ingredients to this, at least in the power industry. And one of them is, of course, a good team of researchers, and I believe we could contribute to that with a couple of years of experience, and with I would really say all the main players in the Hungarian power industry as partners in recent research and development and innovation projects, and also some international collaborations. But also a very important ingredient to this goal that we have set ahead of us is a very good laboratory, which allows us to, or the partners that who are working with us, to achieve very short time to market periods and to turn ideas into products in a very fast and accelerated way. And in the power industry, that requires a good laboratory. And I will just show you this this laboratory in the next slide. The main point here is that this is an infrastructure that has been built in the last couple of years, and this is really rarely found in Europe. I mean, there are infrastructures, there are similar laboratory infrastructures around Europe, but not many of them. And I've just had a PhD student traveling across Europe and looking at various university labs, and he was the one telling me that this infrastructure, he hasn't seen similar in Europe so far. I know there are a couple of others, but he hasn't seen any similar so far. And also some of my colleagues have been visiting a German laboratory of development for a large Chinese solar inverter manufacturer. This lab, the development lab, is in Germany, and colleagues have visited that lab, and they said, yeah, they are working with the same equipment that we are working with. So it's quite up-to-date technology that we have here. And the main point here, the main idea behind this lab is that it's hardware in the loop capable. So at the heart of this, do I have? Okay. At the heart of this this laboratory is this real-time simulator. Right in the middle, real-time simulator, which is capable to simulate the power system, and you can actually do that in real time. Real time means whatever happens in, I don't know, 50 microseconds in reality, the same happens in the simulation, which makes it possible to attach physical devices to this simulation, so that these physical devices really feel themselves or have the impression that they are really in that physical environment that they will be deployed to later. And this is a huge breakthrough in power system simulations. So you can test new types of controllers, new types of measurement and other devices, and also power devices like like solar inverters. And all these devices will have the impression they are really sitting in that field that they are going to be deployed to. And this makes the whole the development process very fast, and you're able to do some rapid prototyping of new ideas and new concepts. So here are some of the devices that I've been talking to. Interesting point of this in this slide is that this whole laboratory environment not only comprises the power system, but also the info communication system behind it. So the SCADA system, the measurement and the data acquisition system, which is an integral part of the power system, and we are able to do simulations and investigations in both of these layers. Okay, so what are we using this lab for? And then I would like to just give you some of details, not very deep details on the project that we are doing recently. These are mainly focused around integration of renewables, of course, but also to develop new concepts and new devices also that help this integration. First project I would like to talk about is batteries. Batteries are becoming a key component in the power system in the recent 1 or 2 years now, at least in Hungary. And more batteries are deployed, and battery operators have the problem that they don't really know if they cycle their battery and ramp up and ramp down their batteries and charge or discharge the batteries at various rates in order to participate at different markets. They don't really know how that will affect the lifetime of the batteries. So they cannot really build a proper business model for that. And they lack this information from the manufacturers. So we are trying to fill this gap by producing a digital twin for various battery technologies. And the digital twin means that we are measuring real-time data, what is available from the battery, and we are trying to model the inner life of the battery and look into the state variables in the battery, and then try to estimate this relationship that I was referring to. And this is what we are doing with different technologies and with different partners now, right at the moment. And we have achieved very nice results validating these models against, well, published literature data also, but we have also our own measurements. So I think this is one of the candidates of ours that we would like to progress into some product in the couple of coming years. Another interesting research, well, it has not so nice relevance to recent blackouts in Spain and Portugal. Blackout means that power system is down, and then it needs to restart it again. And this restart, this black start processes usually do not involve the renewable energy sources because they are not considered reliable enough to be included in such processes. But there are times during the day, or there are, well, actually many hours where in some cases this inclusion might actually really speed up this restoration. And therefore we, with University of Ljubljana and also KU Leuven, we investigated how this would be possible, how we could include, for example, large solar farms into these black start processes. And it turns out it's a very interesting topic and not very straightforward, because it can come to very, here you can see in this figure, very unstable conditions. So the key point of this restoration process is how to avoid these instabilities and which switching strategy to choose, which order of attaching new generation sites to the existing grid and growing the grid again. This is the key question, and this is actually solvable with some Markov decision processes, which are some intelligent technology to find good decisions based on partially stochastic decision parameters. And another project that we are doing for MVM Group, at the moment we have a large cooperation ending actually October this year, and one of the products of this research is a new device that we developed at a prototype level in the lab. And this new device is basically an intermediate device between grid and the load. Normally the load is directly connected to the grid, but we are inserting a new device in between them. And the purpose of this is to separate what's happening in the grid, to separate it from the load, and to be able to provide clean and nice and standard compliant voltage for the load, regardless what's happening in the grid, because there is a lot happening in the grid that we don't want to penetrate to the load. And also, this comes with, this device comes also with some very nice benefits, because it requires less transistors, less elements, and in comparison, if we do all these functionalities, integrating solar, integrating electric vehicle chargers, integrating static storage, instead of all these devices separately, we put it into one single device, and then we achieve some reduction in components as well. So we could make it cheaper, I believe. And also, I believe that time is going, and also world is progressing into the direction that more and more power electronic devices will be built into the grid. And one of the uses, another uses of such a device, such a low voltage back-to-back converter that we have designed here, is well, connecting to low voltage feeders, which is not at all possible today, and it's not done today. But with this device, we could connect these two feeders, starting from the same transformer, starting from different transformers, but we can connect it together, so we can make a meshed grid instead of radial feeders, and that would have the benefit of a better voltage regulation. So in the end, it would be one of the devices that Palma told us about, one of the devices that would be able to integrate more solar devices, more solar panels, for example, to the grid. Okay, and that's my favorite, actually. That's the most far-fetched research area that we are involved in right now. It's like when someone told you, about Tesla maybe 20 years ago. That's something that we're trying to explore in this project, and we are basically redefining the basic concept of power system operation, and moving away from the single frequency, 50 Hertz frequency voltage that is one of the basic concepts in the power community now, and we are moving towards a multi-frequency power transfer concept, which means we are changing the voltage shape, we are adding more frequencies to the voltage shape, and thereby we are able to, I mean, if applied in reality, we would be able to increase the PV hosting capacity by 100%. That means doubling this is a huge number. So if you tell that to distribution system operators, this number alone, they will be really interested, and they are. But this again requires power electronic components, and we have designed these components, and we have shown in the laboratory in a prototype level that this is possible actually, and it's I believe a really interesting topic to follow up and use in the future. Okay, once again, there are many other projects that we are dealing with right now. Our goal is to, well, our vision is to make the power system suitable for increasing 100% supply based on renewable energy sources. Part of that vision is that the system is moving from traditional usual components towards more power electronic components, and we believe that Hungarian companies have a word in that and could become innovative enough to play in the field of large international companies here. So thank you for your attention.